Welcome back. For section 2.7, we are going to do something just a little bit different. We're going to actually do notes on a separate page, this packet that you should have gotten in class. And we're going to do part of it today, and then you'll do the second part of the video tomorrow. You're responsible for 5 major types of parent functions, or types of functions, and being familiar with how they move around the coordinate grid based off of different things that get added or subtracted or multiplied in that parent function. So for example, the linear function is something you're very familiar with. It is y equals mx plus b. And this is something you've seen frequently before, but the most basic form of the linear function is y equals x. And so hopefully you remember what that looks like. Y equals x has a y-intercept at 0, 0. And so one important point here is 0, 0. And then it would have a slope of 1, so it would rise 1, run 1, and then would continue on in a straight line here. So another important point is 1, 1, and then it would go up or down based off of the slope. So you multiply by m. And so in this case, our most basic linear function here is this line here. Now, of course, this line can change. It can be moved left, right, up, and down, and we're going to talk about what that looks like. There's some patterns to how things move, and getting used to that pattern is going to be really important. If something is moved left, so for example, if we did y equals, let's say, x plus 4 inside the parentheses here, adding 4 to something causes it to move to the left. And so in this case, I was originally at 0, 0. I'm going to take that point and move it 4 places to the left. 1, 2, 3, 4. And then my slope didn't change. It's still going to go up 1 over 1. And so this same graph moved left 4. Moving right would be like subtracting. And so if I wanted to move the graph to the right, for example, I could do x minus 2. So one example of that would be I'd take my 0, 0 point, and instead of moving it to the left 4 like I did on last time, I'm going to move it right to here, and I still went up 1 over 1. I got this. Okay. So one thing to think about is moving to the right 2, if I took away my parentheses, was like putting my y-intercept at negative 2. So moving right 2 and down 2 essentially are the same thing. Same thing here. Moving right 4 is about the same as moving up 4 if I had graphed this more carefully. So let's do moving up. So a really simple way to move the graph up is to do y equals x plus 2. Just adding something to the x. Notice here I don't use parentheses. Moving left and right I use parentheses. Moving up and down I didn't. Now it doesn't really matter for linear functions, but it will matter later on. So my 0, 0 point gets moved up 2, and then my slope is the same. It's going to be rise 1, run 1. And I've got this graph right here. And the last one that we'll do on this page is moving down, and that's pretty straightforward. Y equals x minus 1. Again, no parentheses. I would take my 0, 0 point and move it down 1, and then I would still go up 1 over 1. And then I would connect my dots. So linear functions, moving left, right, up, down, is all based off of the values here. We'll talk more about when the slope is multiplied by a number greater than 1 or less than 1 on the next video. So flip to the second page. At the top of the second page, I want you to record that our new parent function is the absolute value function. Now we talked about absolute value equations, but we want to talk about graphing the absolute value function. And so here our function is f at x, remember f at x and y are interchangeable, equals a times the absolute value of x minus h inside the absolute value plus k. Next to that, I'm going to do a semicolon and just say that my easiest one is to say that y equals the absolute value of x. And so, as with most of our parent functions, the absolute value function starts at 0, 0. If I plug in 0 here, the absolute value of 0 is 0, and so that's an ordered pair, 0, 0. So my floating point is 0, 0. If I plug in 1, the absolute value of 1 is 1, and so that would be here. So 1. And then if I plugged in negative 1, the absolute value of negative 1 is also 1, and so that would be here. The format of an absolute value function is a V. And we draw up here. My lines aren't as straight as they should be, but you get the right idea. It should cut through. This is the line y equals x that starts at 0, 0. This is the line y equals negative x. So 1, 1 and negative 1, 1. And then it continues on that way. And so knowing what the parent function is in these three major points are going to allow us to move this, this function around on the coordinate grid. So for example, if I'm going to move it to the left, I could say y equals the absolute value of x plus 2. Adding 2 inside here causes everything to move left 2 spaces. So left 1, 2, it's going to move my 0, 0 to right here, and then we go up 1, right 1, and up 1, left 1 to keep the same format of our V. Here, so let's try moving to the right. If adding inside the absolute value causes something to move to the left, then subtracting would cause it to move to the right. So x minus 3 is going to move us to the right 3 spaces. So that's 1, 2, 3. That's my absolute value right here, or the vertex, the point of my absolute value function right here. And then it goes up 1, right 1, up 1, left 1. So at this point, we should start to get used to the shape of an absolute value function. It's a V. Moving up is if I add or subtract something, and for up it would specifically be adding, but outside the absolute value. So if I take my whole function, the absolute value of x plus 4, for example, I'm going to take that vertex and I'm going to move it up 4. So I'm going to take this and go up 1, 2, 3, 4, and so then up 1, right 1, up 1, left 1, and so my absolute value kind of goes off the graph here, but it's been moved up 4. You can probably understand that moving something down would be the opposite direction. So the absolute value of x minus, let's say 1, would move it down 1 from the 0, 0 spot. And then I'm going to go up 1, right 1, up 1, left 1, and it keeps going. Okay, so when I add something inside the absolute value, it moved left. When I subtracted something inside the absolute value, it moved right. Adding something outside absolute value moves it up. Subtracting outside moves it down. That pattern will continue with our next parent function, which is the quadratic function. The quadratic function is of the form y equals a times x minus h quantity squared, and the squared is what makes it quadratic, plus k. If I subtract something on the inside of the parentheses here, I'm going to be moving to the right. If I add inside here, I move to the left, and then the k causes me to move up and down. So let's talk about what the quadratic function really looks like. Just like before, our standard quadratic function is y equals x squared. So let's focus on this for just a moment. So if we have y equals x squared and I plug in 0, 0 squared is 0. So just like these other ones, we start at the point 0, 0. You're going to notice that that happens every time. Then, if I square something, so 1 squared is 1, 2 squared is 4. So if I go out 2, I would go up 4. Over here, I'm going to go negative 1 squared is negative 1 times negative 1, that's a positive 1, that would be here. And negative 2 squared is negative 2 times negative 2, that is a positive 4. What you're going to notice about the quadratic function is that it's symmetric around the vertex. So I could draw a line down here as an axis of symmetry. But knowing these basic points is the most important. And so we've got 1, 1, 2, 4 are my other points, and then the symmetric points, negative 1, 1, and negative 2, 3. Knowing those will help me get my graph organized. So let's say, for example, we want to move to the left. Moving left requires us to subtract something inside the parentheses. So I'm going to say y equals the quantity x minus, let's say 2 squared. I have to keep the square because that's what makes it a quadratic function. So if I'm going right 2, that puts my vertex right here at 2, 0. And then we went out 1, up 1, out 2, up 4. And then over here I could go out 1, up 1, out 2, up 4. and draw in my quadratic function. As you might guess, moving to the right is very similar, but instead of subtraction, we'll put addition here. Y equals the quantity, let's say x plus 1 squared. So that's going to take the left 1, and put my point right here, and then I'm going to go out 1, up 1, out 2, up 4, and then same symmetry, and draw in my parabola, which is what we call the particular graph. Now, adding and subtracting inside moves us left and right. Subtraction to the left, addition to the right. It seems backwards. It will always do that on the inside of the parentheses. Moving up, though, would be something like y equals x squared plus 2. Here, I'm going to take my vertex of 0, 0. I'm going to move it up 2 spaces. And then I can put in my other points. I got 1, 1, and then out 2, up 4 would be 1, 2, 3, and 4 is kind of off the graph, but I'll go ahead and try to graph it. And then my symmetrical points means that my graph is going to look something like this. This is more of a U shape than my absolute value. And then to move down, I could say that y equals x squared minus 3. Again, the minus 3 is on the outside of the parentheses. It's not part of what's being squared, so it's a down. 1, 2, 3. Out 1, up 1. Out 2, up 4. And then my symmetrical points. Just move my parabola. Okay. So the square root function looks like a U with the vertex at 0, 0, and then some additional important points. We've got 2 more. We've got the square root function, which is y or f of x equals a times the square root of x minus h plus k. The minus h part is under the square root, the plus k is outside, and then over here I've got the standard one as the square root of x. Now we talked a little bit about the square root function before. We're going to start at the point 0, 0. The square root of 0 is 0, and just like all of our other ones, we start here. The square root of 1 is 1, so I'm going to put my next point at 1, 1, just like a lot of the other ones did. But where it goes from there changes up just a little bit. I can't evenly take the square root of 2 or 3, so I'm going to jump to the square root of 4. The square root of 4 is 2, so that's going to be right here. And if I wanted to get really creative, the next perfect square is 9. The square root of 9 is 3. I mean, I can graph. Okay. Now, we talked a little bit about the fact that there shouldn't be any values. You can't plug in a negative x. If you try to grab your calculator and do the square root of negative 4, it would give you an error. So we had 1, 1. We had 4, 2, and 9, 3. Not all of those are going to fit on a graph, but we'll make this work. So if I add or subtract something underneath the radical, then that's going to shift me left and right. So I could say y equals the square root of x minus 2 is going to take my whole graph and shift it left. Plus 2 is going to move me left 2. Then we went 1, 1, so up 1 over 1 from there, and then out 4 from there and up 2. Gives me my up. Same idea down here to move to the right. The square root of perhaps x minus 1 is going to move me right 1. So my origin or my vertex is going to be here. What was 0, 0 is moved right 1, and this one moves right 1, and then my 4, 2 moves right 1 as well. See what I'm doing? There we go. Moving up would require me to add something outside the radical. So these were, again, under the radical. So y equals the square root of x plus 2 is going to move up 2. So if we were at 0, 0 before, we're going to go up 2. And then from there we went up 1 over 1. And then out 4, up 2. And then moving down would be something like y equals the square